Hi everyone, in this video we are going to talk about the models of chemical bonding. So we were done talking about atoms, their different properties. Now it's time to talk about how atoms combine with each other to form the substances that we know and we are familiar with. Alright, so as a review, we talk about the different trends, the atomic properties, and the trends in the periodic table, so which is primarily summarized by this illustration. So if you can remember ionization energy, that's the energy required to take the valence electron from an atom, okay, to remove the valence electron of an atom. And then for electron affinity, that is the energy that was released once an electron is incorporated into the electron cloud. All right, so atomic radius, that's basically the size of your atom, and then metallic character, non-metallic character. Okay, um, electronegativity also, we talked about it, but it has a certain value that we need to take note of. So for this lecture, we are going to describe how atoms form compounds, either ionic or covalent, but in this time frame, we are focusing on ionic bond formation. Okay, so explain the process of ionic bond formation in light of atomic properties and represent ionic bond formation through Lewis electron dot structures, or what we commonly know as LEDs. So you know that chemical bonds, these are primarily the glues, okay, that keep atoms together. So it's the attraction that holds atoms or ions together in forming compounds. Okay, when you talk of ionic and covalent bonding, so I hope by now that you know the difference. Okay, ionic bonding is participated by a metal and a non-metal, while covalent bonding is participated by nonmetals. All right, and then metallic bonding is a kind of a special type of bonding, but the key idea here is if you have metals participating with another metal, then the electron cloud is pulled and then the electrons are being delocalized, meaning they are transferring, they are moving, okay, to and fro, they are actually passing around the lattice. So there is an attraction between the sea of electrons with the cationic lattice. Okay, the cationic arrangement of positively charged particles. So, just an illustration, you have here the three models of chemical bonding. So, ionic bonding made up of ions, covalent bonding are primarily made up of nonmetals, while for metallic bonding, so it is an attraction between the positively charged ions or the cations with the electron C, okay, with the sea of electrons. Now we start with ionic bonding. So you have here the tagline taken not shared, and then we are going to relate it to how that bonding happens. So what is taken or what is not shared. So we first talk about ion formation. So for a neutral atom, okay, it has two possibilities, okay, 50-50. It can either lose electrons or it can either gain electrons. Now we know very well that metals tend to lose their electrons and form cations, while nonmetals tend to gain electrons and form anions. Alright, so cations are positively charged because they lack electrons. Okay, remember that the charge of an electron is negative. So if you take something negative from a neutral atom, it becomes predominantly positive. Okay? Well, as for neutral atom forming an anion, it's mostly for nonmetals. Okay, and what happens here is that there is a gain of electrons. So once you have a neutral atom and it gains something negative, so there is a net charge which is negative. We call that anion. Right? So here is a video from Fuse School to help us visualize the concepts.
We have previously learned about the formation of ions. Now we will learn about ionic bonds. Ions, as you already know, are formed from the loss or gain of electrons. Electrons, however, do not suddenly appear or disappear. They are in fact transferred from one atom to another. Let's look at sodium chloride as an example. Sodium loses one electron to form a sodium ion. The electron is not lost, but transferred to chlorine to form a chloride ion. So we have a sodium ion and a chloride ion. They are oppositely charged ions and will be electrostatically attracted to one another, much like how opposite poles of a magnet are attracted to one another. This electrostatic attraction is an ionic bond. Sodium chloride is an ionic compound because it is held intact by ionic bonds. The same thing happens with magnesium and oxygen. Why don't you grab a piece of paper and a pencil and draw the resulting ionic compound, magnesium oxide? Please pause the lesson and resume when you are done. Magnesium transfers its two valence electrons to oxygen, forming a magnesium ion and an oxide ion. The resulting ions are electrostatically attracted to one another, forming an ionic bond. Did you get this right? Did you remember to include the charges on the ion? Now, let's look at calcium and chlorine. Calcium loses two electrons to form a calcium ion. One of these electrons is transferred to a chlorine atom, and another is transferred to another chlorine atom, forming two chloride ions. The calcium ion is electrostatically attracted to the two chloride ions because the opposite charges must fully balance each other out. In all three examples, the resulting ionic compounds have an overall neutral charge because all charges are fully balanced out. In summary, an ionic bond is defined as the electrostatic attraction between oppositely charged ions. When an ionic compound is formed, the charges must be balanced so that the resulting ionic compound has an overall neutral charge.
Okay, so in summary, or the key ideas from the video is that an ionic bond is an electrostatic force of attraction between oppositely charged ions. So you have a cation and an anion. Okay, ions result from the transfer of one or more electrons from a metal to a nonmetal. Okay, and then you know very well why metals tend to lose electrons to form cations, and why do nonmetals gain electrons to form anions. That has something to do with their stability. All right, so metals tend to get rid of their valence electrons in order to attain the configuration of a noble gas. And we know that if you have a full valence shell composed of 8 electrons or 2 for very small elements, then we consider that atom to be stable. Now, in terms also of the nonmetals, so when nonmetals gain electrons, they are actually filling up their valence shell such that they will have the configuration, okay, of the noble gases. So they must have 8 electrons in their outermost shell. Now, in terms of the atomic properties, so you have here the differences between a metal and a non-metal atom. Okay, so in terms of size, the metals are generally larger, okay, or larger than non-metal atoms. So if you remember the trend, our largest atom is actually that of francium. Okay, now ZF means the effective nuclear charge, which has something to do with the atomic size. But in terms of ionization energy, so let's talk about first the metals. Since the metals are way larger than nonmetals, meaning to say the valence electrons are far from the nucleus. Okay, that means it will be very easy to remove that electron, to remove the valence electron. Okay, and if it is that easy to remove the valence electron, that means it will take lesser energy. Okay, and then we remember that the energy required to remove an electron is called ionization energy. So for metal atoms, ionization energy is lower, okay, because of its size, because of the atomic property or atomic radius. Okay, but in terms of electron affinity, all right, electron affinity, remember that these metals here, these guys here, want to attain a full shell, okay, a configuration like that of a noble gas. So what happens here is it is easier for them to get rid of their one or two or three electrons than to add six more or five more. So for example, calcium. Calcium will be stable if it attains the configuration of either krypton or argon, the noble gas. So what can it do? Which one would take lesser energy? Is it for it to lose two electrons, so 1, 2, such that it will reach the electron configuration of argon? Or would it like to have six more electrons in order to complete its octet? So if you chose removing two electrons, then that is correct. Okay, so metals tend to get rid of their electrons to attain a full shell. All right. Now, non-metals are the opposite of the metals. Okay, so they are smaller in size and they have higher ionization energies because their valence shells or valence electrons are nearer to the nucleus and they experience a stronger pull because of their distance, of the proximity. Okay, but in terms of electron affinity, EA, so non-metals really tend to just receive electrons from the metals. Okay, they receive electrons because, for example, fluorine. So in order for it to become stable, it must follow the configuration of a noble gas. So it can either have one more electron added to the electron cloud such that it will have the configuration of neon, or it can remove, okay, it can remove the seven electrons such that it will have the configuration of helium. And which one is easier? Which one would take lesser energy? Okay, it's the first option, which is to add one more electron so that it will attain the configuration of a noble gas. Okay, so meaning to say the nonmetals have higher affinities for electrons compared to the metals. All right. So in terms of energetics, these are the conditions needed for an ionic bond to form. Okay. So generally, chemical bonding occurs only if it results in a decrease in potential energy. By now, if you have started atomic interactions and if you look at the graph in the simulation, you will notice that there is really a dip in energy, making there is a minimum value of potential energy. And that is basically chemical bonding only happens to have a lesser energy in order for the compound or the atoms in that compound to become stable. Okay, so if there is too much energy between them, they become very reactive and bonding may not happen at all. All right, so when chemical bonding happens, there is generally a decrease in potential energy. The same thing with ionic bond formation. Now, the process is exothermic. That means the atoms must release energy. Energy must exit the system. So that's why exothermic. Okay. But then there are a few considerations. Cation formation, when a metal forms a cation, di ba, you remove an electron. So in order to remove that electron, you must apply energy to it. You must, for example, heat it until it becomes vaporized, until it forms a cation. So the process is endothermic, meaning you supply energy to the atom, to the metal. Okay, and then why is that? Your hint will be in terms of ionization energy. So metals usually have low ionization energy, but you must supply, okay, you must supply that energy such that the electron will be removed. All right, so that is in terms of cations. But in terms of anion, Okay, anion is exothermic, so it releases energy because as the electron is incorporated in the electron cloud, in order for it to become stable, it must lose, the atom must lose some of that energy. Okay, so and that energy that results from the addition of a new electron is what we call electron affinity. All right. So remember that cation formation, once you form cations, you need energy to be incorporated, to be supplied to your atom. Okay. So endothermic energy goes in. Well, for anion formation, energy is released. Okay, in order for the ion to become stable, and then the energy that was released is measured in terms of the atom's electron affinity. Okay, so how can this happen then? Okay, cation formation is usually more endothermic than anion formation is exothermic. So meaning the amount of energy needed to be supplied is greater than the amount of energy that was released. So why then is ionic bond formation exothermic? Eh? Why did we say that chemical bonding happens or ionic bond formation is usually exothermic? So we must add another concept there called the lattice energy. Okay, so just in a nutshell, the once ionic compounds form, they particularly arrange themselves such that the electrons or negatively charged atoms or ions will be attracted to the positively charged ions, the cations. Okay, so they form an orderly arrangement called a crystal lattice. All right, so a crystal lattice is a three-dimensional geometric arrangement of particles. Now, we have an energy associated with them, okay, that is in terms of the formation and the breaking, so we define it as our lattice energy, the energy required to separate one mole of ions in an ionic compound. So in a crystal lattice, each positive ion is surrounded by negative ions, and each negative ion is surrounded by positive ions. Now the thing here is, the main point is, once you form a crystal lattice, okay, once you form a crystal lattice, you need to make it stable. And how can you make it stable? The compounds must release energy. All right. So imagine that when there are cations and anions floating and they are gaseous, so in order to form solid ionic compounds, it must release the energies of those components. So that is what makes the ionic bond formation an exothermic process. Okay, so potential energy lowering happens due to the attraction of anions to cations. Again, in order to form the solid compounds, the the ions must be losing their energy, must be releasing it into its surroundings. So that's why it's highly exothermic. Okay, ionic bonding will only result when the lattice energy is more exothermic than the sum of the electron affinity and the ionization energy, okay, which makes it endothermic. So even if you have an endothermic process going on because of the cation formation, then once the compounds form a crystal lattice, okay, they must release a large amount of energy. Okay, so that is our lattice energy. It spells the difference. It is what makes ionic bond formation an exothermic process or an energy releasing process. Okay, and you might have noticed this in the video where making table salt. Diba? In the video, you have sodium metal reacting with chlorine gas. Okay, and what is our evidence there that energy is being released as the bonds are formed? One is that we have light. Okay, energy was released in the form of light, and number two, in the form of heat. Okay, so it was a very exothermic reaction. Energy was being released in order to form that common, the white substance, table salt. Okay, now, we also need to represent the formation of ionic bonds through leads. So there are actually three ways. One is through the electron configuration, another is in terms of the orbital diagram, and the other is through leads, the electron dot structures. So you know very well how this happens for electron configuration. So remember, for lithium, it has the electron configuration of 1s2, 2s1, right? 1s2, 2s1. So if it forms a cation, it loses this one electron such that you are left with 1s2. Okay, or it's represented here, 1s2 na lang siya, but it has a positive charge. And then for fluorine, so let's say example lithium and fluorine, so we know that fluorine has an electron configuration of 1s2, 2s2, 2p5. Okay, but what happens in the ionic bond formation is that the one electron from lithium transfers to fill out, to fill out the orbitals of fluorine. So it can be seen here in the diagram. So the 2s1 electron transfers here such that the fluorine ion will be formed, and in so doing, the fluorine atom has a full octet, okay, or a full orbital. Okay, if you're going to complete this, then you have eight electrons in the outermost shell, or it follows the configuration of neon. All right, so this is just relating electron configuration and orbital diagrams to uh, ionic bond formation. So in the next video, we will be showing the representation of ionic bond formation through electron Lewis structures, or the LEDs, electron dot symbols. Okay, so stay tuned for the next video. So it is primarily skill based, so I'll be using another platform for this. All right, so for now you can stop and then take your break.